This video we're going to be talking about section 2.4, which deals with functions. So what is a function? So a function is a relation where each element of a first set, let's call that first set X, aligns with or points to a single element of a second set, and let's call that second set Y. Now there's two definitions that, or I don't know, terms that relate to a function, and that is the domain and range. So the domain is made up of all elements of each set X, and the range is made up of all elements of each set Y. So we can sometimes think of the domain as what goes into the function, or the input of a function, and we can think of the range as anything that gets output from a function. So let's just look at a couple examples to kind of hammer home the idea of a function. Now what we see here is four different relations, and what we want to know is whether each relation is a function. So let's look at this first one, and let's suppose that this relation is relating individuals and their birthdays. Now when we talk about individual people, each person has a single birthday. Now what we see here is what's happening on the left here, we can call that the input or the domain, or X. Each item in X is a different person, and these people have names A, B, C, and D. Now what's happening is each person on the left side in X has a different birthday in Y. Okay, now it looks like person B and person C share the same birthday. Let's call that birthday 3, but that's okay. If you think about it, two people can have the same birthday. So this relation, we would say, is a function. However, moving over, what we see is that in the domain X and the range Y, these two individuals, or rather, individual C is pointing to two separate birthdays. Now that does not make any sense. It makes sense that two people could share the same birthday, which is what is happening between A and B. They share birthday 1. However, one individual C, is pointing to two separate birthdays. Now this is not possible for a relation to be a function, so we would say this is not a function. Okay, and if we think back to the definition of a function, each input element can only point to one output element. And what was happening here is element C is pointing to two different output elements. And then the last two relations, let's suppose these relations are showing individual people and their height. Now, similar to the second example, what we see here is that this person, let's call him person -1, is pointing to two separate heights. Now that doesn't really make sense. One person only has one height. So because of this, this is not a function. In other words, each element of the domain does not point to only one element in the range. And then lastly, what we see here is that these two individual people, they share a height. Now that makes sense, right? Two people could have the same height. So what we would say here is that this is a function. Now another way that a relation can be expressed is with ordered pairs. For a list of ordered pairs to represent a function, remember each input can only point to one output. So let's look at all the inputs. The inputs are -1, 1, 5, and -1. Now, does each of these individual inputs point to only one output? Well, the first three are good because we have different inputs, but what we see is when we look at this ordered pair and this ordered pair, -1 is pointing to, in the first case, 2, but in the second case, -1 is pointing to 3. So this input, -1, it's like pointing to two separate values. That tells us that this is not a function. Okay, and then let's look at one more example of ordered pairs. Here we have relation S, and looks like we have 4 ordered pairs, and each of these ordered pairs has a different input value, and each of these input values is pointing to an output value. Now it looks like the input -2 and the input +2 points to the same output, but that's okay. The same output could come from 2 separate inputs, right? This is, again, kind of like 2 people sharing the same birthday, or 2 people having the same height. This is allowed by the definition of a function. So what we would say here is that set S is a function. Now, how do we evaluate functions? Well, first of all, we can write functions algebraically with this notation. How we would say this is g of x. That's how we would read this. So what this says is g of x equals x squared minus 6x plus 8. Now what we want to do is we have this function. It's named g, and the input for this function is right here. So currently we are inputting x into this function. Now in this first example, what we want to do is take the function g and we want to input 3. So what we're going to do is wherever we see an x in the original function, we're going to input 3. So in place of x, we'll put 3, so 3 squared minus 6 times 3 plus 8, and then we just want to simplify down. And doing so, we end up with -1. Let's do the same thing with the next one. We have the function g. We're going to input 1/2. So we would have 1/2 squared minus 6 times 1/2 plus 8, and then simplifying down, and we end up with 21/4. All right, 2 more examples here. In number 3, we're going to input x plus h into the function, so we get x plus h squared minus 6 x plus h plus 8. Now this one's slightly different because we're putting an algebraic expression, x plus h, into the function, but things are still going to operate in the same way. So we just simplify. So x plus h squared, we multiply those binomials, distribute the -6, so -6x minus 6h plus 8, and then simplify it. And at this point, we don't have any like terms, so that's as far as we can go. And then lastly, g of a plus 2, so let's input a plus 2 squared minus 6, a plus 2 plus 8, and expand and simplify. And we end up with a squared minus 2a. Next, let's talk about the domain a little bit more. Previously, we said that the domain is all the inputs for a function. Now, if we're given a function, we want to be able to state what all of those domains are. So a little bit more of a rigorous definition for domain. So we're going to say that the domain is the set of real number inputs that result in real number outputs. So it's the numbers that we are allowed to put into the function. And these numbers must be real numbers in both cases. So we input real numbers, we get out real numbers. This just means no complex numbers or imaginary numbers, nothing that has an I in it. That's what we're talking about. So nothing that has I in it. That's what the restriction is for the domain. So there's 3 categories we're going to talk about when we're talking about the domain. We're going to talk about polynomial functions, rational functions, and radical functions. And each of these we treat differently when we're finding the domain. So let's talk about polynomial functions first. By polynomial function, we just mean a function that just has polynomial terms. So something like this would be an example of a polynomial, nothing too fancy. So a regular polynomial function has variables, it could have variables, but it doesn't have any square roots where the x is under the square root, and it doesn't have any fractions where x is in the denominator. So here 1/3 is a fraction, but x is not in the denominator. This allows us to say that this is just a polynomial function. So the domain for a polynomial function is always going to be all real numbers. No matter what the polynomial function is, the domain will always be all real numbers. Now there's two ways we can write this domain. One way is in interval notation, and in interval notation we write all real numbers as negative infinity to positive infinity with parentheses. The second way that we can write the domain all real numbers is in set notation. And in set notation, how we would see this is we have a curly bracket. We say all x such that x is equal to all real numbers. So this r, it's just kind of like a bolded r with those two vertical lines. This is how we would express this in set notation. So how we would read this is all x such that, well, how about I don't abbreviate, such that x is all real numbers. The next type of function is a rational function. So a rational function, again, is just a function that has the variable in the denominator of a fraction. So here are two examples. G of x equals 5 over x plus 2. H of x equals x squared plus 5x minus 2 over 3x squared minus 5. So g of x and h of x, these are both examples of rational functions. So how do we find the domain of a rational function? So we want to make sure that no matter what value we input for x, that the function is still defined. Now when we have a fraction, like what we have here, these fractions are going to be undefined when the denominator is equal to 0, because we can never divide by 0. So to find the domain, we want to know what values are going to make that denominator 0. And whatever makes the denominator 0 is not in the domain, but everything else is in the domain. So how do we find the domain? So to find the domain for a rational function, what we do is we set the denominator equal to 0 and solve. So the domain would be everything else, and we'll see how this works when we do a couple examples here. Okay, so set the denominator to 0, solve the equation, and then the domain is everything else except what makes the denominator equal to 0. The last type of function is a radical function, and a radical function is a function, well, that has a radical, and specifically where the input variable is inside the radicand, so underneath the radical. So how do we find the domain, or what is the domain for a radical function? Similarly to a rational function, the domain of a radical function is all real numbers except what makes the function undefined. So we want to avoid whenever the function will be undefined, and for a radical function to be undefined, this is when the value or the radicand is negative. So we need to figure out what makes the radicand negative, and that is what is not in the domain, and everything else is in the domain. So how do we go about finding this? The easiest way is to find out when the radicand is greater than or equal to 0. So the domain is this expression, the expression that is greater than or equal to 0. So that's it for this video. I don't want to make it too much longer. In the next video, we'll go through a bunch of examples, seeing how we can actually find the domain of these different types of functions.